Okay, today we're going to take a look at trapezoidal approximations. And yes, we're skipping over 5.2, 5.3, and 5.4 because I feel like the trapezoidal rule really does follow with the rectangular approximation methods that we did in 5.1. Again, why? Well, these are approximations. They're not the exact way to find the area under the curve. So let's review real quickly a trapezoid. So usually when we think of a trapezoid, we think of it in this kind of a position where the height is perpendicular to the two bases. And we have base 1 and base 2. And the area is going to be height over 2 and then base 1 plus base 2. Now what we want to do in this lesson is we're going to look at, let's say I look at from here to here, and I want to look at the trapezoids involved. So what that means is I'm actually looking at a trapezoid that's on its side. So kind of like take this one and imagine here is the picture of our trapezoid now. So here's the height, and here's base 1 and base 2. The area of this is still going to be the same. So in our last lesson, when we were looking at the base of the rectangles, that was the subinterval length. This time, our height is the subinterval length. And the two bases are the height, or the y value on the function. Okay, so here we have this graph, okay, and I look at, all right, draw a line straight up, and I look at that trapezoid. I draw a line straight up, I look at that trapezoid. Here and here. Okay, so what ends up happening with the trapezoidal rule, especially if they're evenly distributed, so these are all the height. So here's base 1, and then here's base 2. But then base 2 happens to be part of this trapezoid as well. So imagine if I had to add all of these together. I'd have h over 2 base 1 plus base 2 plus h over 2, and then I'd have this one would be base 2 plus base 3 plus next one would be h over 2 base 3 plus base 4. And then this last one would be h over 2 base 4 plus base 5. So if you notice, these were all used twice, whereas the ones on the ends were only used one time. So they were duplicates. So that's where we get the trapezoidal approximation method. We have two choices, kind of like what we looked at last class. You can either do individual rectangles. Okay, we use that, like when we did this last example, we did individual rectangles because they were not evenly distributed. Or you have this trapezoidal approximation. Okay, and we'll look at the formula for this on the next page. Let's look at an example where we're just going to create the different trapezoids first. So again, what had I mentioned? The height is the length of each subinterval, and the bases are determined by the function's value. Okay, so we want to approximate the area under the curve f of x equals 1 over x from 1 to 5. So I'm looking at this region here. Here's my region. It's from 1 to 5 with 4 subintervals of equal length. So kind of like what we did yesterday with the rectangles, or the last class. So we have 5 minus 1, and there's 4 subintervals. So basically each height, right, from 1 to 2, this is our height, is going to be 1. So from 2 to 3, from 3 to 4, from 4 to 5. So we're picturing these, right, trapezoids connecting. Okay, so my trapezoidal approximation, the first one, so we have h over 2, so 1 over 2, and then we have, so base 1, so I'm going to plug in 1, so that's going to be 1 over 1, actually let me use parentheses, 1 over 1 plus 1 over 2. Right? I'm just plugging in 1 and I'm plugging in 2 and I'm plugging into the function 1 over x. So that's going to be the area of this first trapezoid. The second trapezoid, also height of 1, so 1 over 2. Base 1 is 1 over 2. Base 2 is 1 over 3. So that took care of this area. Next, from 3 to 4, so our height is 1 over 2. Base 1 is 1 over 3. Base 4 is 1 over 4. So I took care of this third trapezoid. And finally the last, so we're looking from 4 to 5. So the height is 1 over 2. Base 1 is 1/4. Base 2 is 1 over 5. So we want to plug that into our calculator. And let's see. And you'll notice if you have the same height, the 1/2, you can multiply that all at the end. So 1 plus 1/2 plus 1/2 plus 1/3 plus 1/3 plus 1/4 plus 1/4 plus 1/5. So we get about 1.683. So the approximate area under the curve is 1.683. Now, as we noticed, and this is one of the things I had mentioned previously, the ones on the ends, here and here, get used once. All the others get used twice. So we can actually simplify this to this formula. So we have h over 2. So we have y sub 0 and y sub n are used once, and all the interior heights are used twice. Okay. Again, this is on a closed interval where they have equal length, and that's how we know the height is going to be the interval length divided by the number of partitions. And if a quick way to check, if you wanted to do LRAM and RRAM and average them, that's actually the trapezoidal approximation. Okay, so example number 2, we are going to refer to the region enclosed by the graph of the function between the function y equals square root of 2x and the x-axis from 0 to 8. So let's go ahead and graph that. So 0, 0. If I plug in 2, I get 2. If I plug in 8, I get 4. Again, it's just a rough sketch. So here is my region, R, and we want to use the trapezoidal rule using 4 subintervals of equal length. So that means my height is going to be 8 minus 0 over 4. So each height is going to be 2. So I go here, here, and here. So I'm going to use the shortcut, this formula here. So I have the height over 2, so that's why I'm going to have 2 over 2. And then, remember, my function this time is the square root of 2x. So I'm going to plug in the values I'm going to plug in. I'm going to plug in 0. I'm going to plug in 2. I'm going to plug in 4, 6, and 8. So when I plug in 0, I'm only going to use that one time because that was an endpoint. This one, I'm going to plug in twice. So I have the square root of 2 times 2. 4 is also used twice, so I'm going to plug in 2 times 2 times 4. 6 is also used twice, so 2 times square root of 2 times 6. And then square root of 2 times 8 is only used one time. Again, what this is from the formula, this is y sub 0, this is y sub n, and these are all the 2y sub 1 plus 2y sub 2 plus 2y sub 3. That's the implication there. So when we multiply this all out, we're going to get 20.585. Next one, refer to the region R enclosed by the graph of the function between the graph of y equals x negative x squared plus 4. So let's see, that's going to look like, so at 0 we get 4, at 1 we get 3, at 2 we get 0. So it looks like this. Okay, and it goes from 0 to 2. And we want to approximate this with 4 subintervals of equal length. So this time the height is going to be 1/2. So that means here's a half, here's 3 halves, so I'm looking at the trapezoids created here. So I have height over 2, so 1/2 divided by 2. Again, I'm going to use 0 and 2 once, and the other 3 I'm going to use twice, and that's by plugging into this formula. Again, really what I'm going to be looking for this on quizzes and tests, I'm going to look for the setup. Okay, I'm not so concerned about the actual value. What I'm going to explain to you later is on the AP exam, you can actually leave your answer, you know, in this form where you're just adding them all together. Usually they don't ask you to find the sum. So it's more of the setup that's important here. Okay, so let's plug in 0. So I have basically negative 0 squared plus 4. And then I'm going to plug in 2. And I want to have negative 1/2 squared plus 4 plus 2. And then I'm going to have negative 1 squared plus 4 plus 2. And then negative 3/2 squared plus 4. And then I'm going to use 2 just one time. So it's going to be negative 2 squared plus 4, which happens to end up being 0. So we add all that up, and we get about 5.25. Okay, use the function values in the curve, in the following table of the trapezoidal rule with n equals 5 to approximate the area under the curve from 0 to 5. So kind of similar to when we had table of values with the rectangular approximation method, here we have trapezoidal rule. And we want n equals 5, so from 0 to 1, 1 to 2, 2 to 3, and 4 to 5. And so we can do this with trapezoidal rule, or we can write it out with individual trapezoids. This one, I'm going to just write, since the height is 1 for each of these, I'm going to do height over 2, and then it's going to be 10, and then it's going to be 2 times 16, plus 2 times 18, 2 times 20, 2 times 14, plus 10. And for this, we do get 78. Now the next example, we can't do that same way. The reason is the heights are changing. Here the height is 2, here the height is 1, the height is 3, 2, and 2. So I'm going to have to set up separate trapezoids this time. So recall h over 2, base 1 plus base 2. And remember the function's value, these are the bases this time. These are the heights. And again, when I say the heights, it's the difference in the time interval. So the first height is 2, so we have 2 over 2. Base 1 is 5, base 2 is 6. Plus, next one is height of 1 over 2, and then 6 plus 11. Next height is 3, so 3 over 2, and then it's 11 plus 15, plus, and then it's 6 to 8, so that's 2 over 2, 15 plus 12, plus 2 over 2, and then 12 plus 10. So we're going to add all that up. So we have 5 plus 6 plus half times 6 plus 11 plus 3 halves times 11 plus 15 plus 15 plus 12 plus 12 plus 10. So I get 107.5. Okay, example 6. An observer measures the outside temperature every hour from noon until midnight. Recording the temperatures in the following table, what was the average temperature for the 12-hour period? So first thing we're going to do is we're going to look for the net total of basically the temperature accumulations. So we're going to treat n as 0, midnight is 12. So if we look here, the heights are all 1. And so let's write out our trapezoidal approximation. So it's going to be 1 over 2. So it's going to be 63 plus 2 times 65. It's going to be all of these times 2. So I'm just going to put them all in here. So you can do this as well just to kind of save a little time. And then 55 is used once. So when we multiply this all out and add everything, we get 782. So that's the accumulation of temperatures over that time interval. So notice that we asked for the average temperature. So the average temperature, we want to divide 782 over the total number of hours that it was. So when we talk noon to midnight, so for 12, so we get about 65.167 degrees. Okay, example 7. The table below records the velocity of a car in miles per hour at different time intervals over 20 seconds. Use trapezoids to approximate the total distance traveled and the average velocity. Okay, so total distance traveled and average velocity. Again, there's differences in the units. This one's time in seconds. This is velocity in miles per hour. So we had one with the rectangular approximation method in the last notes like this. So let's start with our trapezoidal approximation. So we look at our time interval and we see, again, we have the situation where it's not evenly distributed. So we're going to have to set up different trapezoids. So the first one is 0 to 3, so the height is 3 over 2, 13 plus 27, plus, next one goes 3 to 7, so that's 4 over 2, 27 plus 46, plus the next time interval goes from 7 to 9, so that's 2 over 2, 46 plus 50, plus, then we go 9 to 13, so that's a 4 over 2, 50 plus 44. Then we go 13 to 16, so that's 3 over 2, 44 plus 52. Next we go 16 to 17, so that's a half, 52 plus 54. And finally 17 to 20, that's 3 over 2, 54 plus 60. Okay, so let's add that all together. So 3 halves, and then 13 plus 27, plus 2, and then 27 plus 46, plus 46 plus 50, plus 2, and then 50 times, plus 44, plus 3 halves, 44 plus 52, plus a half, 52 plus 54, plus 3 halves, 54 plus 60. So I get 858. So that's the total distance traveled. So the total distance traveled. Now we have to change the time unit. So remember, 3,600 seconds is equal to 1 hour. So we actually want to take 858 divided by 3,600. And we get about 0.2383. So that's going to be miles. Or if we multiply that by 5,280, we get 1258.4 feet. And then if we want the average, we take 858 divided by the 20 seconds, and we get about 42.9, and that's going to be miles per hour. We don't need to change the units because if we go back to that accumulation, that was in seconds, and that's why we change it with the miles per hour, but we just divide by the 20 seconds total. And so total distance traveled versus the average velocity.